I'm sorry, I have some technical issues.
Listo, Cristian. Ya estamos.
Ok, gracias.
¿Podrían compartir el link de YouTube? Así lo comparto también a otros.
Dale,
Gracias.
Está en el chat.
Muchas gracias.
Voy a empezar de vuelta. I'm going to start again to see if it works now. Sorry, I have some technical issues.
Listo,
Yes.
Cristian. Ya estamos.
Ok, gracias. I don't know why it wants to stay here.
¿Podrían compartir el link de YouTube? Así lo comparto también a otros.
Ok. ¿Ya lo compartí yo? ¿You will share that? Ok, muchas gracias. I'm going to hide this.
Teresa, por favor, recordá apagar el micrófono.
We're more or less okay. Yes, it's not easy. But well, I think everything is prepared. I can show the laser, which is important, and I can go forward. Can I go forward? Can I go forward? I can go forward and backward. Okay, perfect. Yes, we are ready. Sorry for that. So. Thank you. Yes.
Okay, so good afternoon to everyone. So we have a pleasure this afternoon to listen to your defense. So Mr. Christian Marcelo Martín.
Yeah, that's it.
So I'm the chairman of your jury. So I'm tesis function. I'm from University of Study and so in the jury. So unfortunately, I'm at the zoo, so I'm going to present them. So I will start with the so first, Professor Guido Musso, Professor Christian, and my wife is Antonin Frederick, the research professor at UNTPU. And so from the Zoom,
Yes.
we have the Professor Maria Belén González from Patagonia.
That's it.
She's professor at Universidad da Coruña. And here Professor Diego Manuel. Yes. political demanding. Hierarchical Pesu is research director at MPC. Research professor Teresa
That's it.
Universitatea Tehnologia tesis de recherche Universitatea Tehnologia SA. And Your PhD, okay. So you have 45 minutes to work, and then after discussions, so up to the
Okay, well, thank you very much for that introduction. Well, let's just begin. Got the nervous that I have. So, good afternoon, and thanks to everyone for being here. I am Christian Marcelo Martín, and today I'm going to present you my PhD, the work that I have done in my PhD thesis, which is called, as you can see there, Mechanical Properties and Microstructure of Lightweight Well Cement Paste for CO2 geological storage. This was a co-supervised thesis done both at, well, here, École Nacional de Ponts et Chaussées, and in Argentina at the Universidad Nacional de Patagonia, San Juan Bosco. My supervisors are all those listed there, which are Jean-Michel Pereira, here, Diego Manzanal, also here, and Sebastián Gabezo and Teresa Piqué in the video. So, let's begin by the beginning, which is understanding what is this CO2 geological storage. In general terms, it's a climate change mitigation technology which aims at avoiding emitting this greenhouse gas to the atmosphere and instead inject it into deep reservoirs. For doing that, this fluid is injected in supercritical states, which is achieved for this material at temperatures higher than 30 degrees centigrade and pressures higher than 7 megapascals. This is only reached in reservoirs that are located in reservoirs at depths larger than 800 meters. So in these conditions of high pressure, high temperature, and abundance in the environment of CO2, it is important to assess the integrity of the whole system. In this regard, we have two main scales, the reservoir scale and the well scale. Among these two, I'm going to focus on the well scale. In this, we have to distinguish two parts, which is, okay, it works. Here, the injection, the possible injection well for CO2 and the possible legacy wells, which are abandoned wells. As you can see in the image on the bottom there, you will see that each of these wells is formed basically of three parts. We have the formation rock, we have the internal metal tubing called casing, and then we have the interface between these two, which is the cement shed. Among all of this, it is important to assess in this well scale the cement shed integrity. For doing that, well, we have to take into account the objectives that this cement shed has, among all of which I'm going to center and to make a focus on providing sonar isolation. Since these cement sheds can already generate some potential fluid migration path for the CO2. It can form microannules, cracking, or even the transport of this CO2 through the cement matrix. In this regard, it's important to know how this cement is placed there by the cementing operations. So the cementing operations are done when the cement is placed in is in fluid state as a slurry, and these conditions has to verify the same conditions, the same requirements as the drilling mud, which are that the cement slurry pressure, which is directly related to the slurry, to the cement density, should at every depth be higher than the pore pressure, but lower than the fracture gradient. This is a measure of the strength of the rock formation at each depth. In particular formation rocks in which this fracture gradient is low, then we will have possibly the need of using lightweight cement slurries. There are many alternatives to achieve this lightweight material, among which we can distinguish, for example, those listed there, which are increasing the water to cement ratio or using foam cements. These are well known for increasing the porosity, particularly intergalactic porosity, and affecting the general performance of this material. So we are choosing in this research work here, replacing cement partially with hollow glass microspheres, which is a lightweight material. What are the main properties of this material? Well, they consist of small particles, they have a density that is very low, and they have also high strength. So many good properties. But since we are replacing partially cement with the spheres, we have to know what influence this sphere may have on the cement paste. For this purpose, I'm going to focus on two main aspects, which are the Fourier effect and the Bosonian activity. For understanding this, we have to understand basically what the cement hydration is about. So what we have is that the clinker is composed of tricalcium silicate and dicalcium silicate that will react with water during cement hydration to form calcium hydroxide and calcium silicate hydrate. So knowing that, we know that these spheres may present some Fourier effect, which in the context of this thesis, not in the scale of the sphere, but in the scale of the hydration products, this may act as nucleation sites for cement hydration products, which will increase the kinetics of hydration and also improve or increase the compactness of the material. This is at short curing time, but then at long curing time, we can also have a Bosonian activity. This is known as a chemical reaction between the silica of in this case, the spheres, and the calcium hydroxide from cement hydration to form secondary CSH. This is also a chemical reaction very well known for increasing the compactness of the cement matrix, which a priori is a good thing. But the cement will not only be subjected to these conditions of being partially replaced with the spheres, but also to the conditions existing in a CO2 injection or legacy well. In this regard, we have to take into account cement paste carbonation, which is basically this idea presented here, in which calcium hydroxide and CSH will react with carbonic acid to form calcium carbonate water and lixiviated silica. This will also result in a change in porosity and a decrease in the pH due to the consumption of calcium hydroxide. This will be important later on, that's why I'm focusing there. In general terms, we can see that from the research here of Kuchko and Barria, this is there is a propagation of the front of this cement carbonation in which we have an inner part which is mainly unaltered, and then we have an outer part which is more altered by this exposure. So, with all of this taken into account, we can now establish the main objective of this research, which is being able to assess the performance of this lightweight well cement paste, in which we replace cement with the spheres, for CO2 geological storage. For reaching that main objective, we have three different objectives. The first one is related to assessing the properties of the cement with the spheres in terms of microstructure characterization and mechanical properties. Then we have to assess the changes in the property, in these two properties, due to the exposure to supercritical CO2 conditions. And then finally, we will end with a verification of the suitability of this compound material and lightweight material in the context of CO2 geological storage well or injection or legacy wells by numerical modeling. So, having said that, here I present you the general outline of the presentation, in which I have two main parts. First, I have the experimental characterization part, which I will be talking right now. Then I will have the modeling part. And finally, I will have some conclusions and perspectives related to this work that I'm presenting. Advancing to the experimental part and to analyze or to show you the materials that I have been using, I have three main materials, which are hollow glass microspheres called HEMS27, which will be from now on the green one here. Then we have HEMS41, the blue one, and there in that table there, you can see the main properties of these two hollow glass microspheres. First, the very low density of 280 and 460 kilograms per cubic meter, the mean particle size of 30 and 40 micrometers, then the strength, which gives them the name, 27 megapascals for HEMS27, 41 megapascals for HEMS41, and then we have the content of silica, which is high in both of them, and this is related, if you remember, to the Bosonian activity, which is around 60% for both of them. Finally, I have used class G cement, which is a moderate sulfur resistant class of cement, which is manufactured according to the 10A standard of the American Petroleum Institute and has a density much larger than that of the spheres, which is around 3,000 kilograms per cubic meter. As for the specimens that I have been using throughout this thesis or this project, we can distinguish these 6 different specimens. In the first column here, you will see the plain cement paste, the red ones that I have been using. The only difference between these two presented there is the water to cement, in this case, ratio, which is 0.44 from the one on the top and 0.60 for the one on the bottom. There you can see that on the name, 44 here and 60 there. Then 00 stands for no replacement of cement by colorless microspheres. And then you will see that we have these 2 other columns of specimens in which we have the first one in which we replace partially in 10% in weight cement by spheres. So that's why the name goes with 27 there. And the last one is 41 because we have done the same, but with colorless microsphere 41. Then we have obviously the same water to solid ratio. And it is worth noting here the differences that we obtain already in terms of density, where we go from 2,000 kilograms per cubic meter to around 1,400 kilograms per cubic meter here. So we had an important increase in density, which is important in the context of lightweight materials. And we did that also in terms of the changing the water to solid ratio. So with this said, I want to show you the methodology that I have followed in my PhD program. And I have 3 main parts. The first one related to the interaction between the spheres and the cement paste. For this, I have done these experiments there, or tests there, from which I'm only going to focus in this presentation on the thermogravity test and the modified Chapelle test. Then I have 2 other parts in which I have not only analyzed the influence of the spheres into the cement paste, but also the influence of the carbonation, for which I have done the microstructure characterization and mechanical properties with the tests that are shown there. Also in the numbers there, you will see the number of tests of each of the tests performed in each of them. I have talked about carbonation, and for doing that, what I have used is this carbonation cell that is present here at the École Nationale de Pont-et-Chaussée, in which I was able, as you can see here, to put my cylindrical cement specimens and then subject them to high pressure of 20 megapascals and high temperature of 90 degrees centigrade in a CO2 saturated atmosphere with the presence of water. And there, we were able then to measure the properties just before carbonation. Here is a cross-section of one of these specimens before the carbonation, and you will see that it's all purple, indicating with this pH indicator that the pH is higher than 9. So there it was before carbonation. And then we will see that after carbonation, we will have something like this, in which the outer part, as it was in the researches of Kuchko and Barrian, is more affected with a low pH related to carbonation, and the internal part is purple, which indicates that it was mostly not altered by this exposure. After this taken into account, I'm going to present you now some of the results obtained in this first experimental part. And I will begin by analyzing the chemical interaction, or the interaction between the spheres and the cement paste. For this purpose, we will begin by the thermogravity test, in which I was able to measure the content of calcium hydroxide. To have an idea of the test, it's just a test in which we measure the change in mass of a little sample as temperature increases from around 20 room temperature to 800 degrees centigrade for the apparatus that we had. And this difference here, which is highlighted, is related to a mass loss that corresponds to the amount of calcium hydroxide that we have in the cement paste. So with that, I was able to obtain the content of this compound, hydration compound product, which at 7, 28, and 56 days of hydration, of curing time, of the red cement paste being the plain cement paste, the green cement paste, the cement paste with HMS 27, and the blue cement paste, the cement paste with HMS 41. First, what you can see there is that we have very similar results in the 7 days calcium hydroxide content, which, given that we have partially replaced cement with spheres, is an indicative of the possible filler effect of the spheres, since it's kind of presenting a enhanced kinetics of the hydration. If we then take a look at the results at 28 and 56 days, meaning longer curing times, we will see that there is a relative decrease in the content of these hydration products, which could be related to consumption due to the personnelic activity of the spheres, which is reacting with the calcium hydroxide to form secondary CSH. We can try to confirm this with the modified Chapelle test that I have performed, and there, just to understand it, we know that this modified Chapelle test is a direct quantification of the personnelic activity in which we expose these spheres into a solution that has abundance of calcium hydroxide, and we are able to measure the direct consumption of this compound in particular conditions of high temperature. With that, the corresponding standard established limits indicated by this red line here, and we are able to see that both spheres presented higher consumption than that established in the standard. This means that according to this standard, both spheres could be considered personnelic materials, and moreover, HEMS 27 presents higher values than HEMS 41, which relates to a higher personnelic activity of HEMS 27 than 41, possibly due to the smaller particle size of that sphere of 30 micrometers in mean particle size. So, well, with all of this, I tried to show you that there is some filler effect and personnelic activity of these two spheres, and then these chemical interactions are known for improving the compactness of the material. So for this purpose, and analyzing if this compactness was increased, I show you here some MIP and semi-Michis results. There, again, in red, the plain cement paste, in blue, the cement paste with HEMS 41, and in green, the cement paste with HEMS 27. And first, I want to focus on this little peak here with the plain cement paste. And you will see that for these pore entry size diameters, the corresponding paste with the spheres, for the corresponding paste without the spheres, with the spheres, sorry, this peak disappears. This could be related to the sphere effect and personnel activity in enhanced compactness of the material, which can also be seen somehow in these semi-meches here. You can see a less compact material and some metrics here than in the cement paste with HEMS 27 and HEMS 41. Then you will notably see these important two big peaks that we have here for each of the cement paste, and this is mainly related to what we have done related to the rupture of the spheres, which is happening due to the exposure in this MIP test, in which we are reaching high pressures. Sorry. So what I have done here was MIP directly on powder samples of the HEMS, and I was able to see that they began breaking even before 50 megapascals. So this is around the pressure that is indicated here. So this peak corresponds to the mercury accessing this the void space inside the now broken hollow glass spheres. Having understood that, I want to focus now on the carbonation, and for doing that, I first show you some results on the advance of the carbonation. This was done with pH indicator, and there you will see the results for water to solid ratio of 0.44. This first column is the non-carbonated samples, or the cross-section of them. Then we have the second column for carbonated for 60 days specimens, and then the third column for carbonated for 120. The first row, plain cement paste, then the second with the green one, HEMS 27, and the third one with the blue one, HEMS 41. You will first see that the non-carbonated cement specimens all present a perfect coloration, indicating a high pH, indicating that there is no consumption of calcium hydroxide. Then, after 60 and 120 days of carbonation, for both cement paste with the spheres, we see this complete gray cross-section, which indicates that we don't have any high pH there, which is related to an important advancement of the carbonation in this cement paste. So that's something to take into account, and I discussed throughout my work that could be related to the broken spheres that are increasing the interconnected porosity and affecting further this cement matrix due to the carbonation. Then, in the result for the plain cement paste at 60 days, we will see almost an equal purple surface there. But then at 120 days, we see this typical behavior of the results as seen by Kuczko and Barria. If you go to the results for the water to solid ratio of 0.60, you will see for the cement paste with the spheres the same results, this for here, and then you will see that for the plain cement paste, there is an increased advancement of the carbonation, in which already here we have some advancement of the carbonation, which could be related to an increase in the interconnected porosity, which is well known for increase in the water to cement or solid in this case ratio, and a more affection of the carbonation. What we can see there is that we have an inner point which is more affected, and we have an outer point that is less affected. So now I'm going to focus on these 2 points on the following. So if we go to that, I will first show you the results obtained on the plain cement paste. There you will see the solid line that corresponds to the non-carbonated cement paste. Then the slash lines correspond to the carbonated for 60 days in the internal parts, meaning these less affected parts. And then we have the dotted line, which is down there, which corresponds to a sample of the carbonated for 60-day specimen on the outer parts. And what you can generally see there is that both the internal part of the cement sample, carbonated for 60 days, and the non-carbonated cement sample present roughly the same kind of microstructure. Then if we take a look at the results on the external part, you will see a complete disappearance of this peak, which could be related to some precipitation of the calcium carbonates. And also what you can see is that that doesn't change from the different water to solid ratios on the left and on the right. And also what we have, which can be more noticeable in these two cement images here, is that before carbonation, we have more or less more defined cement matrix. And here we have a less defined cement matrix and some calcium crystal precipitation, which is noticeable. If we compare these results to the results obtained for the cement paste with the spheres, we will see something like this. What is interesting about that is that the results of the slash and the dotted, meaning both the internal and the external part of the carbonated specimens, is roughly the same, which corresponds to a homogeneous carbonation throughout the whole specimen. This was also seen in the cement paste with holographic microfilter 41 in spite of the higher strength. So both of these are indicative of rupture that is occurring in the spheres throughout the carbonation exposure with 20 megapascals. And what is also indicative of that is that we are having some loose particles of calcium carbonate that is being that has precipitated already inside the spheres. So up to now, we have seen that we have clear effect and personal activity and enhanced components of the cement matrix, and then we have some changes in the cement matrix due to this exposure. Let's see how this affects the mechanical properties. So for doing that, I will start showing you some results on the confined mechanical properties. This is quite difficult to understand, but I will try to explain it with my best. So there you will see the results in solid line for the elastic, the Young modulus, sorry. Then you will see in dotted line there the results for the UCS. And then you will see the two groups, water to solid ratio of 0.44, water to solid ratio of 0.60 on the right. And you will also see that we have a first group of 3 in each of these figures, which corresponds to the C00 samples, which is not carbonated. And then we have the result for the C60 samples, which corresponds to the samples carbonated for 60 days. What we can see in general terms is that in the first group, there is a decrease in all of these unconfined mechanical properties when we replace cement by holographic microfilters, from this to this, and then from this to this. So we have the lower value of these parameters for the cement paste in which we have replaced partially cement with a weaker sphere. Then what we can also see is that after carbonation from here to here, we have a decrease in all the parameters, in those unconfined parameters. And this happens for all the cement paste. This happens also here, from here to there, from here to there, and from here to there. And what we have is that the larger decrease occurs for the cement paste with a weaker sphere. The green one, the HMS 27. If we now want to take a look at the results of strength obtained on both unconfined and confined compression tests, we will see that, well, here I show you the results of unconfined compressive strength, which I have shown you before. The solid line points correspond to the non-carbonated specimens, and the dotted line points corresponds to the carbonated specimens. Then you will see that, well, we have this lower strength at low sigma 3, but then as we increase the sigma 3, we have a larger extent of the increase in the frictional behavior of the cement paste after carbonation, which can be seen here to here. With this data, we're able to obtain these strength parameters that we will then use in the modeling part, which are the results of cohesion and friction angle for the non-carbonated samples in this table here and the carbonated samples in this table here. You will see that the cohesion here is relatively high and here is relatively low, and then the friction angle here is relatively low and here relatively high, which corresponds to the behaviors in there. So I have talked a bit about modeling, so I'm going to that part now, even though I have already got a bit there. So here we go to the modeling part. We'll start again with the methodology. And there you will see that I have followed this, again, 3 parts, because I like to be repetitive. And the idea here was to make a numerical simulation of the carbonation process in well conditions. For achieving that objective, we have gone first to an estimation of elastic parameters, which was done with this analytical homogenization model I have used, which was considered in 2 cases. The first one is the perfect interface condition, and the second one is the imperfect interface condition. Then I have done some validations with laboratory results, which was done doing some calibration of key parameters. Then I have modeled the conditions attained in the carbonation cell, and then I have validated the results obtained from compression, whether unconfined or confined compression tests. Finally, I have done some modeling under real-world conditions, in which I modeled a slice of the cement annulus, and the idea there was to predict the behavior of this compound material, and particularly to assess the suitability, which is the main objective, of this compound material and lightweight material in these particular conditions. This was done using the Bill finite element code developed by Patrick Dangla from the Université Gustave Eiffel. This is a fully coupled chemoparo-mechanical model, which solves these 3 equations. We have first mechanical equilibrium, then we have a fluid mass conservation, which is mainly the conservation of water, from which I'm going to focus particularly on the porous medium deformation, which depends on the elastic parameters of the porous material, which is the cement matrix. That will be affected by the estimation of the elastic parameters in the compound material. And then we have the Darcy term, which is related to permeability, which will be affected by the rupture of the spheres due to the increased internal porosity. Then we will have the third equation and final equation, which is CO2 mass conservation, which has 3 main terms, from which I'm going to focus on only one, which is related to the diffusivity and permeability of CO2 in cement. This term will also be affected by the rupture of the spheres, which will result in an increase for interconnected porosity of the material. So let's go now to some of the results that I have obtained. And there I will begin by this analytical homogenization model, in which I have used this representative elementary volume shown there, which consists of 3 main phases. We have there phase 1, which is the void space inside the sphere. This can be seen in this very beautiful semi-image there, where you can see a broken sphere, which has its void part in the inside. Then we have phase 2, which is the glass of the outer shell of the sphere, which can also be seen there, this outer part there. And then we have the cement matrix, which can be roughly seen in this image here, surrounding all the spheres. There are presented the main equations of the model, in which we see that the homogenized elastic parameters depend on the volume fraction of each phase, the elastic parameters of each phase, and also this AB and AD, which are volumetric and deviatoric strain localization coefficients, in which we have worked quite a lot. So there, I will show you here that I have done some model calibration. This model, initially Sorry, I'm a bit tired already. Here, initially the model was modified a bit to account for the presence of the spheres, as using the red I showed you before. This was done considering this micromechanical model for an layer composite sphere as developed by Herr and Zoe in 1993. This is the condition of the perfect interface in which these strain localization coefficients depend only on known parameters, which are the elastic parameter of each material, the volume fraction of each material, and then the external and internal body of the spheres. We all know that. Then the model was extended for accounting for imperfect interfaces between different layers, in this case, the spheres and the cement, which was developed already by Gabeslo in 2015. And in this, we have that the strain localization coefficients now depend on these two compliance parameters, which are normal and tangential compliances, which are parameters to be calibrated and account for allowing a possible displacement between in the contact between the sphere and the cement. With this, I show you here, in this first figure here, I show you the results of K experimental in the x-axis and model in the vertical axis. And if there is, and here the sheet results, the shear modulus, experimental in the x or horizontal axis, and vertical is the model results. And if we have a value that coincides completely with the diagonal, then we have a perfect agreement between model and experimental parts. First, I show you there the white points, which are the results before considering the imperfect interface, meaning the perfect interface without any calibration at all. And there you can see already that we have quite a good predictive capability of the model without calibrating anything, leaving it only analytical. But we were able to improve it a bit, considering the imperfect interface and this possible displacement between phases, which is noted here with the black points, in which we can see that they are much closer, both in K and in G, to the diagonal line, which means a almost complete agreement between model and experimental parts. If we now go to some model application, we will see that in this figure here, I'm showing you the results of homogenized bulk modulus and the bulk modulus of the cement paste, or the cement matrix, actually. In the horizontal axis, you will see the volume fraction of spheres, which is increasing in that direction. Then we have this ratio in the vertical axis, which is R2 over R1, which is a representative of the thickness, the higher the thickness. And we will see that as the thickness increases and the amount or the volume fraction of the sphere decreases, we will have increased homogenized bulk modulus, which is expected since we are reducing the amount of void inside the spheres. So this makes sense. Well, so up to now I have shown you the results on this analytical estimation of elastic parameters, and I want to see what will be the application for this, and for doing that I will go on with some validation of the model. For doing that, as I told you before, I'm considering two cases. The first one is the cell of the CO2 cell, the cement carbonation, and the second one is modeling the triaxial compression tests and validating the results. So first here, what we have is the carbonation cell. This is the geometry that I have adopted. It's, in general terms, it's a rectangle with an axis of axis symmetry here, and then another axis of symmetry down here. And region 2 and 3 indicated there represent the external edge of these cylindrical specimens. I have applied the conditions corresponding to the carbonation cell, which are CO2 concentration in regions 2 and 3, confining pressure and fluid pressure in these two regions. With this, I was able to obtain some results, but not before calibrating this important parameter here, which results in the effective diffusivity that we obtained in the model. This effective diffusivity, which is this parameter here, relies on this parameter that I have calibrated for all the samples. I have used the same value of the parameter, and also accounts for the porosity that we have on the cement paste, on the cement matrix, actually. So let's begin by the results obtained in the calcium hydroxide volume fraction all across the cement specimens in the plain cement paste. So there you will see that we have a pattern of colors indicating that in the most inner part we have roughly an unaltered cement paste, and the outer part we have a more altered cement paste due to carbonation. But we never reach a zero content of calcium hydroxide, which is more or less what we obtained from the pH indicator test, where the outer part didn't appear to have a low pH, so we can relate that there. Then I want to show you the results obtained for the HMS 27 cement paste. And there you will see that we don't have this anymore, this pattern of colors, and instead we have a complete blue coloration, indicating, as you can see in the scale there, a zero concentration or volume fraction of calcium hydroxide. This correlates very well with the results obtained in the pH indicator test, where we have a complete consumption of calcium hydroxide. And this happens because we have also included this possible fracture of the spheres. The spheres broke during these conditions of 20 megapascals, using the results obtained in the MIP on powder samples. And then this porosity here increased, and this affected the effective diffusivity. So it was easier for the CO2 to transport within the cement matrix and affect the whole cement matrix there. But then it is worth mentioning that we are having some interesting results for cement paste with HMS 41. Well, there you will see that we have a pattern of colors more or less similar to that presented in the plain cement paste. In fact, we have even less consumption of the calcium hydroxide. And this could be related, and will be discussed a bit more later, to not arriving to being able to break the spheres, because the input data is the result that we have from HMS on powder sample, on MIP on HMS on powder samples. So with those results, 20 megapascals doesn't reach the breaking pressure. So the spheres are not being broken, and this parameter is not being affected. So that's it. Let's see what we obtain from the compression strength. There I have again the same geometry, of course, but the difference are the conditions in which I have applied confining pressures in region 2 and 3. Then I have fluid pressure and deviatory pressure applied in region 3, which corresponds to this part of the machine. With this, I have obtained some results of deviatoric stress against strain for different conditions. We will see first that these conditions, I have to mention this, it's important, were obtained, these results, with the calibration of a stern parameter that I have shown you before of cohesion and friction angle. And there, first, you will see in this first figure here that you have in solid line the results of the non-carbonated cement specimens on the unconfined compressive strength. Then the dotted lines corresponds for the same cement paste, the non-carbonated cement paste, but with a confining pressure of 30 megapascals. Well, then here we have an increase in the deviatory pressure, of course, but then what we see is that we have the same stiffness regardless of the confining pressure that we are using for this plain cement paste, the red one. If we go to the other extreme, which is this one here, the HMS 27 cement paste, we will see that we have an increased strength of the material, but there is a decrease in the stiffness. And why is that? Because we are applying the confining pressure. During the confining pressure, the spheres are breaking. Since the spheres are breaking, they are transforming somehow into porosity, and this decreases in the homogenization model the stiffness of the material. Then, in the cement paste with HMS 41, we have somewhere in the middle, because we didn't break that many spheres, so we are having some behavior in the middle between these two. If we take a look at the results obtained on the other image, on the image on your right, you will see that here we have the results for 30 megapascals on confining pressure on the carbonated specimens on internal point in solid line and external point in dashed line. So let's begin by the easiest, which is the red one. And there you will see that the inner part presents a lower stiffness than the outer part. This is related to the precipitation of the calcium carbonate crystals in the outer part due to the more extent of the changes in this outer part. And this, since the calcium carbonate is more rigid, it will increase the stiffness of this part of the material. If we now go to the other extreme, which is this one, we will see the contrary effect. And the problem here is that we are having a coupled effect of both the precipitation of calcium carbonate, but also a larger extent of the rupture of the spheres. So here, let's say that the rupture of the sphere is winning. Then here in the middle, with the stronger spheres, we have something in the middle. Not winning the calcium carbonate precipitation, not winning the sphere, the broken spheres. Neither. So with this, I have validated the results that I have obtained in my laboratory tests. So now I will model the well conditions. Here I present you, as I have presented you before, and this is the general geometry I have used here, in which I have changed it a bit. I have again a rectangle, because it's easy, and then I have in the middle an axis of axis symmetry, but it's located in the middle of the well. Then we have region 4 there, which is the internal edge of this slice of cement annulus, which is in contact with the casing of the well. Then we have region 2, which is in contact with the formation rock, which is there. And then we have regions 3 and 1, which are in contact with the other slices of cement. The conditions applied there corresponds to a slice of the cement shed located at 1,000 meters depth in the well, which are 10 megapascals of fluid pressure, and then a confining pressure applied all in regions 1, 2, and 3 of 25 megapascals, and then a concentration of CO2 in region 2 in the external edge. So with this, I'm only going to show you some results on the variations in the volumetric fractions of each phase present in the cement with the spheres. Let's begin by plain cement paste, again, because it's the easiest. So first, in blue, you will see the results, the consumption of the calcium hydroxide during carbonation, which is the first that is happening here, which results in a precipitation of calcium carbonate, which is the orange phase there. Then, once the calcium hydroxide is completely consumed, we begin by the consumption of the calcium silicate hydrate, and this results also in an increase in the calcium carbonate phase there, and the lixiviated silica in light blue there. We also have, which is interesting to note, a slight decrease in the porosity, which is this red line there, due to the higher molar volume of the calcium carbonate with respect to the cement hydration products. Okay, let's now go to the cement paste with sphere 27. And there, well, it's not so easy to see, but we have some rupture of the spheres at the beginning when we apply the conditions. Here, which resulted in this volume fractional sphere, which is a little decreased. We increased a bit the porosity, but then it resulted the same as we obtained in the plain cement paste. So generally speaking, the diffusivity is the same, but we have less volume fraction of cement. So in this cement paste here, the kinetics, or let's say the advance of the carbonation was complete earlier than in the plain cement paste. If we now take a look at the results with the cement paste of with HMS 41, we will see that we are not able to break the spheres at all. Then we have a decreased porosity, which decreases the diffusivity of CO2 in the cement matrix. And then with these conditions here, we see that the carbonation occurs slower than in the plain cement paste, with a cement paste with hollow glass microspheres, which make the cement slurry and the initial part lighter, which is the best of both worlds. Well, we have to mention that this could be a limitation of the model, since we are not taking into account the positronic activity of this sphere, which may consume the outer shell made of glass of this hollow glass microsphere and affect, as it did, as we measured, the strength of the material, which let us break it in the carbonation cell, but here we are not able to break them with these conditions. So, to end, here I present you some conclusions. And first, related to the experimental parts, we have these three main groups of conclusions again: the interaction between the spheres and the cement paste. We are able to measure the Fourier effect and positronic activity, okay? And we are able to measure also the increased compactness of the material. In terms of microstructural characterization, we are able also to measure the influence of the exposure to CO2 injection and legacy wells conditions, which reduce the pore entry size peak that appear due to the calcium carbonate precipitation. And also we have seen that the rupture of the spheres affected a lot the advancement of this carbonation process. Also, this affected the mechanical properties. Initially, we have seen that the spheres already affected quite a lot, the mechanical properties decreasing the unconfined compressive and Young modulus. And then we have some reduction in these unconfined mechanical properties due to carbonation. And finally, we have seen an increased strength, increased frictional behavior of the carbonated specimens after carbonation. In the modeling parts, we have obtained within modified homogenization model a good predictive capability with a perfect interface already, but we were able to improve it a bit. We get into errors that were even lower than 5% in absolute value. We were able to account for the rupture of the spheres, which affected both the interconnected porosity and the diffusivity of the CO2 in the cement matrix. We were able to calibrate some key parameters to obtain the results obtained in the lab. And finally, we were able to model the exposure to CO2 in injection and well and legacy well conditions. And there we have to take into account the thing that I mentioned you before, which is this limitation of not considering the positional activity and the consumption of the sphere outer part due to the positional activity. As for perspectives, I'm only showing some of them here, which are investigating the extent of this sphere consumption during the positional activity, which could be done, for example, by nano indentation tests. Then it would be nice to explore the frictional behavior of carbonated cement specimens, which could be done by an exhaustive campaign in triaxial drain tests. Then it would be interesting, as we did with the elastic parameters, to develop a model, an analytical model, to account for to model the strength of this composite material. And finally, it will be interesting to integrate in the chemopore mechanical model the damage related to chemical and temperature exposures. To begin with, I want to keep talking. To end, I want to acknowledge all these institutions. First, the universities, the Universidad Nacional de Patagonia, San Juan Bosco, and the École Nationale de Pont et Chaussée. Also, the labs in each of these institutions, here, Laboratoire Navier, and all the people here, which really helped me a lot for this thesis. Also, in the Instituto de Tecnología y Progreso en la Tecnología in Buenos Aires, they helped me a lot there. And then all the financing institutions there, which helped a lot to carry on with this project. So, well, that's all. Thank you very much. And I think I'm sorry for the slight delay. Thank you for listening. Yes, maybe I was a bit pressed. Yes.
So we have just some seconds just to have a break.
Okay, yes. Thank you very much.
So just to say a few words, because just to recall that your thesis is a joint thesis in the Economics Universidad Nacional de la Patagonia.
Yeah, that's it.
Okay, and so it's okay now.
It's okay? Yes, I can relax a bit. Yes. Okay, thank you. Yes, I was a bit pressed to finish in time, so well, yeah, that's.
So we start by discussions and first Professor Guido Busto
Bueno, felicitaciones, me gustó mucho.
Bueno, muchas gracias.
Now I go in English because
Yeah,
I have
okay.
to be official, but I liked the work when I was reading it, and it was very complete. And also, I appreciated a lot the fact that there is it is really multi-physical, so you are taking into account a bit of let's say the chemical aspects, a bit of the well, mechanical, of course, because we are geotechnical engineers. And then there is modeling and laboratory. So I know it is a complex task to carry on all the things all together. No? So this is why I think that your thesis is very good, because there are all these aspects of it. I have a few questions.
Yes.
I
expect
this is my job.
Yeah. Okay, I understand.
So one is that I wrote you this in the comments, right?
Yes.
And I wasn't very sure how the exposure conditions were done in the carbonation cell. So if you can describe it a bit more.
Yes, so just to be more, to explain it a bit deeper. I had, as I showed you there, maybe I can go there if you want,
This is
or...
slide 11.
Okay, yes. Good that you have taken note of it. Yes. Okay, here as well, right? I mean,
Okay.
well, I will go to
Yes,
11.
that one is okay.
Okay. Okay, there we go. So there, it was the carbonation cell. I had put a bit like some centimeters of water in the bottom before putting my samples. And there I put there 18, if I remember well, 18 samples or specimens of cement. And finally, I closed the cell and I started injecting the CO2. This was done until reaching the pressure that was in the tank of CO2, which was around 5 megapascals or so. And then I started increasing the temperature. So with the temperature, also the pressure increased until reaching these conditions there. So there I reached, with the temperature, I reached 90 degrees centigrade and 20 megapascals. And I kept constant that throughout the whole exposure time, which was 60 or 120 days.
Well, did you write something about it, but you don't explain too much. Did you pay attention maybe to the, let's say, history of pressure and temperature, whether alone they might affect a bit the behavior of the sample?
Well, this is a huge subject, actually. We were able to mention, at some point, we were able to see that there is some changes in the specimens due to exposure to pressure, of course, mainly the cement paste with the spheres because of this issue of the spheres breaking, which was quite an issue to understand. And then in terms of temperature, of course, we have some degradation. Yes, this is degradation due to temperature exposure, but we did not measure it on itself. We have done all together in a couple problem, and that was all.
Yes, of course, I was thinking about the pure cement, because the
other of course,
it is clear that you break the crystals.
Yes, but I wasn't able to do that. It would have been interesting actually, and I have thought about this, but okay, I don't have time to do everything, of course. So well, yes, but it would be nice to take a look at this afterwards.
Maybe with nitrogen or whatever. No?
Sorry.
It might be interesting to have a comparison on the pure cement, or maybe on both of the things, to apply without the CO2, because the CO2 induces carbonation and so on and so forth. No? By taking an inner gas.
Yes. Yes, it will be very interesting. Yes, I agree.
Then there is another thing which it wasn't 100% clear to me, but it's of course with respect to I think the C20, the 27 HMGS, the one with the medium strength.
We have two. We have the higher strength and the lower strength.
The lower.
The lower, yes.
You say something when you refer to triaxial testing, into which at the higher confining stress, at the end you get a smaller strength than the one that the test made at intermediate confining stress. No?
Yes.
15 and 30, I believe.
Yes. Well, I have some results here. I have to go all through the presentation. I will get there soon.
Thank you.
Okay, I prepare this. Okay. It's here. Okay. So there, well, I present all the results. Well, I don't remember. It's here. Okay. So the slash dotted corresponds to the cement paste. So it's CS27. No, this is not. Okay. The solid one corresponds to CS2744 C00 with 30 megapascals of confining. And then the dotted corresponds to the same cement paste but with 15 megapascals. And maybe that's what you're referring to, right?
Yeah.
Okay, yes, what I did mention there is that there is some influence on this difference in the behavior between this one and this one due to the rupture of the spheres, which is actual mechanical
Yeah.
damage that is occurring. So I was referring to that. Maybe I was not clear in the manuscript. But-
This was to start my question.
Okay, yeah, okay, perfect. Sorry.
Because here I wonder
Hmm.
what would be the different effect of the pore pressure and of the confining pressure. I mean, no, let's assume that, for instance, you're doing the test on a dry condition or on saturated condition, you apply a pore pressure. Now the total stress and the pore pressure affect differently the behavior with the skin.
Yes, well, this is quite an issue. I haven't think a lot about that actually, but yes, let me think a bit. Yes, I have to think. Eh?
Well,
Yeah, I mean to start talking. Yeah, it's nice. I mean, if you only had the pore pressure, let's begin by the easiest, maybe. I don't know if it's the easiest. Well, let's see. If we only have pore pressure, it would already, I think, these conditions will be similar to those obtained in the MIP. I think if it's like affecting with fluid everywhere. So I think that in that condition, they will break at the pressure corresponding to the curves that I have obtained. But then, what I understand is that when I reach some effective pressure at each point, then the spheres will break if we have during conditions. But well, I don't have a complete answer for this actually. It's difficult to answer. It's not easy. Yes. With the result that I've seen, I have had, what can I say? I have to think of it. No, it's interesting. Yes. Okay, what I have considered even within the model is that when we reach some effective pressure in a given point where we have spheres and everything, then the sphere with this effective pressure, they will break. So I think that this is correct, and that's why I applied it. But also, if I have some fluid pressure, this will happen. It's quite a complex. Yes.
so in the model, well, this might be actually related to another question. In the model, when you model the breakage of the crystals
Spheres, yes.
of the spheres is related to an effective stress.
Yes.
Right.
Yes.
You link it to the effective stress, which is the normal tertiary effective stress.
Yes.
Right.
Yes, that's it.
And then I have just another question.
Yes.
So I must leave room to other people to make their job. Can you tell me a bit about? I think you were a user of the transport model, no? Because you didn't.
No, I didn't develop. It was just a use of the model. Yes.
Yes, it was already developed.
Yes.
But,
Yes.
Just to understand, you were modeling the transport of CO2 and water, right?
Yeah.
Is it correct?
Yes.
Those were
it's-
the only two species that you were modeling.
Yes,
the
that's
transport.
it. I will have water and CO2. Yes, which is represented in the equations that I presented somewhere at the beginning of the modeling parts. We are almost there. Here. So we have fluid mass conservation and CO2 mass conservation. So
Okay.
there we have the.
Yes. And then the chemical reactions are all chemical reactions at equilibrium.
Yes.
There is not inequity.
Mhm.
do you think, well, I've seen other models into which maybe it might be of interest also to consider the transport of other dissolved species that might react with CO2 or with the solid phases, and also maybe some kinetics in it. But I noticed that you do not consider. Can you spend some word on it?
Yes. Well, related to the kinetics, we do have an equation that I didn't present it here, but we have a calibrated parameter as well that I don't want to enter into confusion here, so I didn't present it, but which is the tau that it's in the manuscript.
Yeah.
I haven't taken it to the presentation, which could affect the kinetics and affected in fact the kinetics of the carbonation reaction. But we are not accounting for the kinetics from a chemical point of view, actually. And what would have been could have been interesting is to account for that, and as well to take into account that, well, here it's a simplification in which I want to show you this, in which we are considering a simplified model in which first calcium hydroxide is being consumed and then calcium hydrate. And this is not necessarily how it happens, it depends. So, well, there are many factors to take into account. I know this is a simplified model to take all of this into account. And we could also have consider, I don't know, for example, the influence of others, exposure that occur in these conditions that may also affect the durability of this material. Of course, yes. It would have been nice, but maybe for future works, it would be a nice.
For your second PhD.
That's it. Yes, yes. Why not?
Okay, thank you.
Okay, I hope I have replied.
Thank you. So after that, let's see the
So, President, so I will try to speak English, so that's easy for me. And so, yeah, first of all, I want to congratulate you for your work, your presentation, to listen, with a lot of experimental results, of modeling, and a lot of very interesting work that has been done. And so, as my colleague, my duty is to ask you some questions. I will ask you some questions, maybe sometime to push you in some place. But it's quite easy for us to ask questions. But for sure, your work is very impressive. So,
Well, okay, thank you very much.
Before I begin to ask my question, I want you to.
Okay. Okay. Thank you for that. Yes.
And, yeah. First of all, yeah, maybe a first general question. So, why carbonation is problematic?
Well, yes. Is carbonation problematic? I mean, that's a question. Yeah, actually.
Yeah.
That's why I said in the perspectives that we have to see what happens with the carbonated specimens at high confining pressure, which are the conditions in the well. Because in terms of strength, we are having maybe with the results that I could obtain throughout this thesis, we have obtained maybe some increased frictional behavior. Also, what we are seeing is, well, here this figure is nice for that because we have a decrease in porosity. So yes, it's not necessarily bad. Of course, yes. That's why I have changed a bit, and that's why I want to thank you, Diego and Jean-Michel, because I have changed the words a bit. I was talking about degradation, and maybe it's not degradation, but only changes on affected and unaffected parts. Yes, because it's not necessarily bad. That's true. Yes. And I know there is a lot of work related not to these conditions, but to more traditional conditions in building and all that, in which they consider carbonation as something of self-repair. So, yes.
And so then, I will not ask my question in the order of the presentation, so because you are talking about the mechanical strength and the behavior of carbonated cement. So at first glance, we can be quite surprised that carbonated samples have a lower compressive strength and a lower Young modulus than uncarbonated ones because the porosity is reduced. And it seems that, from my knowledge, that calcium carbonate are stronger than
Yes.
than Portland. So why?
How to answer that? Yes. Well, let's see. I will go. Where will I go? Let me think. I think I will go to the microstructural parts. Maybe here or here, maybe. Okay. Well, we have mentioned porosity and the increasing porosity and the abundance of calcium carbonate. So that's why I'm going here. Okay, so let me formulate the idea in my head. Okay, first, I want to say that I have researched quite a lot regarding this behavior of the cement paste, and well, different authors publish different results. So this is already an issue. Okay, so these are my results, which could be more or less okay, or could be more or less not okay. So I have to take that into account. Unfortunately, that's it. But for what I obtained, I think that the idea is that we have this, that is the third point there, less defined cement matrix with more loose particles. And I included that there because it's a key phrase. Why? Because what I think and I have thought throughout the writing part of the thesis was that, and the analyzing of the result part, that the cement matrix is, let's say, disappearing, and it's the one that grants cohesion to the material. So that's why we are losing properties in unconfined conditions. But then the loose particles are granting some possibly frictional behavior. So we have a balance there that we have to consider. That's why I said later in the perspective parts that it will be very interesting to analyze this possible frictional behavior with a more amount of triaxial tests that I was able to do within my PhD. And if we do that, we will be able to finally shed light on this. But for now, I can only say some ideas, but nothing for sure.
It's a really big question because in a previous slide I will go on that point, and so we have a lot of assumptions. I'm not sure that one of them are correct, but maybe some crystallization pressure of calcium carbonate or calcium carbonate by precipitate in some places, and the dissolution is on other places. So when they precipitate, so they generate overpressure, or maybe over. Okay. But we don't know.
Yeah, that's it. I mean, I have thought about this idea of the crystallization generating internal pressure. I tried to apply this theory into my results, but it didn't work. So I decided to remove it because it was just making more confusion in a really confusing thing. So, well, yeah.
And what is very interesting is that this kind of reduction of mechanical behavior occurs for supercritical carbonation, but not really for natural carbonation.
Yes.
And so that's why I think it's a big point that maybe.
And there, I think that your comment, Ido, would be interesting in analyzing each thing separately. Maybe we have the CO2 exposure condition, only CO2. Then we can have results on the exposure only on pressure, and then we can have the results only on temperature exposure. And with all of this, then we can couple all together, but this would be a huge work, but well, we can do that, possibly. And with all of that, we can shed a bit of light in this regard, because I'm pretty convinced that there is some degradation related to temperature, which could be happening also.
So I will come back to the beginning because I have some question on the formulation, but I do not understand. So it's really from my understanding.
Okay.
Okay. There is 2 points I have not really understand. The first one is why you keep ratio water to solid content and not water to builder content, because it seems that the water is much more there for the builder than for the spheres. And the second one, I do not manage to understand how you replace your 10% mass. because I make my calculation. I can see 10%. So
You can see, okay.
So or maybe I must be very poor in mathematics because I can't see the 10%. Where they are.
Okay.
How do you manage to
Okay, yes, so I can explain you a bit all of this. So the first thing that we did, as I presented here, was analyzing this sphere effect and mainly the postsonar activity, because this thesis was a continuation of the thesis of my master's degree, in which we have already seen some results, and we were already trying to understand that maybe this postsonar activity was occurring. So we started just like that, by saying, okay, what's the interaction? We could be postsonar activity. Okay, how do we measure that? To measure that, we go to the ASTM C311 first. We went there, and there they state a replacement of cement with the material being tested. So they say, okay, we had initially I think it's 500 of cement initially in the plain cement paste, let's say, and then they have 400 grams of cement and 100 I think it's 20%, and 100 of the material being tested. That, according to them, is 20%. But if you do 100 divided by 400, you will obtain 25%. That's maybe what you did.
Yeah.
So it's not. It's 100 divided by 100 but plus 400.
Wow. Okay.
That's it. And we did that.
It was the response. Okay.
Yeah.
Maybe it would be good to put the calculation on the
Oh,
screen,
okay,
because
yes.
it's a bit confusing, because if we do not know exactly what okay, I was sure that there is something like that, so the reference wasn't a good one, but maybe if you have some time, you can put the
Yeah, of course, I can add
be
some paragraph or equation or something to
it's
include that.
easier to understand your approach.
Yes, yes, sure. Well, yes.
Okay.
Yes, I will do that. Yeah, of course.
And for the for the constant W2S ratio instead of a W2 bigger.
Oh, okay, it's the same actually.
This is to keep the same. Okay.
Yeah, that's it. It's exactly the same. Sorry, I forgot about that question.
Okay, so I had actually the same kind of question on the curing and especially on the why the curing wasn't really under pressure, but there is all the discussion was already been done previously by my colleagues, so we not ask question on that point particularly. But I have anyway another question on the carbonation. Why you use 20 megapascal and 90 degrees? 90 degrees, sorry.
90 degrees.
90
Yes.
degrees. Okay, it's very extreme.
Yeah, it is. It is actually. It is. Well, I told you that I have done my master thesis in this regard. I did a short stay here. So there it started all of this. I think, well, I don't know. Here they started with Valérie Palin and that, but in terms of our group of research, it started there, and then there was another PhD, now a doctor, that did some tests with these same conditions. So the idea was to follow up on these conditions that that he imposed to the material, to have some further results in this, to continue the line of investigation. That's it.
Yeah.
The idea was to subject the specimens to very extreme conditions actually, to be able to assess the properties in these particular and very severe conditions.
Okay. So because before carbonation, so the sample was kept at atmospheric temperature and pressure.
Yes.
And then it was carbonated. So
yes.
I wonder in the real life, okay, in the real life of the slurry, you inject it, okay, in the well, okay, in the space, okay. When the sphere will break, before or after? So because it showed everything, because if it's before hardening, you will not have the effect of low density slurry will not be there anymore.
Totally true.
Yeah.
Well, what I can say there is that during this slurry state, I mean the first state of the cement, there will be no consumption of this outer glass, shell, and all that. So we can trust the results that we obtained through MIP on the powder samples.
At the beginning, yeah.
At the beginning, yeah, that's it. So if we don't get to pressures close to those at which the spheres start to break, then we'll be okay. The spheres will still be there while in the first state of the cement paste, the cement slurry actually. Well, then the cement will harden, and we'll have to see there what are the conditions of pressure and pressure mainly that will possibly break the spheres as time pass by due to the consumption of the outer shell. Yes.
Yeah, but maybe it might be interesting to test. I'm not sure that this test will be so long to do. For one, because maybe if since the beginning it's in pressurized condition, maybe we change. I don't know, but it can change because it can change the iteration with the spheres. Maybe I don't know. Maybe it will increase that or decrease. I don't know what might happen. But
so sorry to understand. Because,
I wonder if maybe the crushing of the spheres, maybe they can be due to because you increase quite rapidly the pressure. Maybe if
it's already there,
maybe I don't know.
Yeah,
it will be interesting to see if there can be a kind of stress.
It's actually interesting. I didn't think about that.
It's only it can maybe not. I don't know, but anyway, maybe the effect of the pressure on the overall system can be maybe different if the pressure was always there.
Yes.
Or if the pressure was introduced after.
Yeah, of course.
Can be. Okay.
Yes.
I'm totally not sure that.
No. Imagine if you're not.
We are discussing.
That's it.
But it will be interesting maybe to.
Yes, sure.
To test that point. Well, I will go on because I will try to. So I've got one test that I wanted to trust. It is on the test that are made to characterize the material. I have two questions on that.
On the materials?
Yeah. The first one is why do not on the material on the ardent slurries. Okay. So you make the MIP test for the size distribution.
So here. No, I think it.
You can stay here.
Okay.
So for you make the MIP test for the microstructure characterization.
Yes.
And you do not do a diffusivity test to see an permeability test. Why they are found to be very important parameters, and why mercury tuning porosimetry? Because and why not, for example, a nitrogen absorption test or water absorption test that can indirectly as well give some kind of pore size distribution, and which think are less
aggressive
yes. In terms of pressure for the system, because sure, but you can see that on IB test, okay, the effective stress remains almost equal to 0 because you put mercury inside and outside. But since you have some spheres, the spheres, they are confined by the mercury. So well, because I think there is this kind of device in
yes.
Yes. You can measure the diffusivity coefficient and the nitrogen absorption.
Yes, I have not the best answer, but I have an answer for that. Well, the best answer would have been not to have this question. So, well, it is there. We began everything with the idea of estimating the porosimetry or the pore entry size distribution with this MIP. And then we started to see these weird, I will say now, peaks that appeared on the cement paste with the spheres. But at that moment, it's not like now, we didn't know what was happening there. So we started to think, it was a discussion of almost a year and a half, about what was that peak there. Then I think that it was you, Jean-Michel, who suggested me to do this MIP on HMS powder. And there we saw that they are breaking the MIP and this whole phenomenon is happening. So yes, it would have been a great idea, but it was too late to do it.
But
That's it.
anyway, it led to a very interesting discussion on the MIP test page, which is very, very interesting.
Yes,
So-
yes, it was necessary.
So from a scientific point of view, you made a really interesting.
Well, thank you. I think I didn't want to do it, but well,
It is science. When we make some. My last question after that, I will have a lot of because your work is so interesting. But I will have. But I will ask. Okay, one last question on modeling because to be sure, how do you estimate the advancement rate of reaction? On the you can put the probabilistic equation if you want. The mass conservation equations.
it must come. Okay, yes. Here.
Yeah.
Yeah.
You know, there is a dxc Ri divided by dt, which is the advancement rate of the reactions.
Yes.
Ri. And so, how do you estimate it? You assume that all the CO2 that come is consumed, and do you assume that there is a sort of sequence between all the reactions? So one reaction will be finished in order to have a new reaction that begin.
Yeah.
Or do you assume that there is some kind of percentage of reaction that can occur together?
Okay, yes.
How do you estimate that?
The chemical part is more or less simplified.
Mm.
So how it works is that it starts by consuming the calcium hydroxide,
Mm.
the ions from the carbonic acid react with this, and once it's completely consumed, then it follows with the calcium silicate hydrates until it's totally consumed, and that's it.
Okay, so you follow the model of Valiant.
Yes.
Okay.
Yeah, that's it. Exactly. So you know.
I think
yeah.
it would be good. It would be good to say it.
I haven't said that. Okay.
Maybe too rapidly, but when we see the question, we do not really understand. Well, maybe when we look at your graph after that, we can see, okay, he should have done that. Because we can see some kind of sequence
here
between all the system.
Yes.
But
it should be mentioned clearer. Maybe.
Yeah,
Yes.
I think it will be good to clearly say it, or maybe you have said it and I
No.
but,
Well,
but
yes, I will take a look at that.
even if you cite the things, it is good that the PhD is standalone. We can have all the information only in your manuscript, and we have not forced to see what's made in
Yeah,
your
of course.
manuscript. Well, it's not
Perfect. Yes, I can do that for sure.
okay. So I will get. Je vais laisser la parole. Give the floor. Give the floor. Okay, I will give the floor to the others, and I congratulate you again for your work.
Well, thank you very much.
Okay, so now the next with Professor Martín.
Yes.
Professor, c'est ça, hein?
Maria
Maria
Belén.
you are there?
Hello, yes. Sorry, I can't hear you very well. The public, the PhD student, I can hear you very well, but not the public, not too much. So sorry if I repeat some questions because I'm not sure if I can hear them very well. First of all, I would like to say that congratulations, because it is a very great job what you have done, because you have developed a very huge experimental program and also the modelical part, the numerical part. So I think it is a very impressive job. And so congratulations to you and also to your supervisor. Thank you for inviting me. It has been a pleasure also to read your work and to share with you and with the public these ideas. First of all, I have some questions, not very, too much, and only a few questions. First of all, I would like to question you to know some of the mixes that you have developed. You have included some superplasticizer in them. I don't know, only in the mixes with 0. I think, if I remember well, with 0.45 water-decimal ratio. And I don't know if you have considered the effect of this superplasticizer, because maybe some of these kind of materials are including some retarded effect, or some even some air entrained in the mix, in the cement paste. So I don't know if you have considered this, and you have think about the possibility of discussing the results, considering this effect.
Okay, yes, this question I was expecting it at some point. So yes, as you mentioned, I have used superplasticizer in this sample and this specimen, sorry, these two. I have used it, I think, in 0.2 and 0.3% in weight of cement. And well, the actual answer is that no, I didn't consider any effect that superplasticizer could have on the cement matrix microstructure. But I only added it to make it possible to mix these mixtures, because I was adding only 10% in weight of these spheres, since they are very light. It's a huge amount in volume. It's like 50% volume sphere and 50% volume cement. So it was necessary to add them to make it possible to mix the slurry. I have considered that the amount that we have used, that I have used, is not large enough to affect that much, at least the properties of the cement matrix, but it could be interesting as well to assess the differences that could come from this superplasticizer. Yes, I haven't done that, but it would be a good idea. Yes, I agree.
Okay. In this regard, I would like only also to suggest you that maybe a replacement by volume instead of by weight would have been better to discuss the results, because as you have said, you are replacing by weight, and it seems the same quantity, but as they have very different density, I think that the quantity is very, very, very different in this regard, in the mixes. You have in this slide that you are showing, you have represent the same volume, and it is not, because you are replacing by weight, so the volume is really different, really different.
Yeah.
Anyway, it is okay. I think that my other question was regarding the carbonation process. I think that some of my colleagues have already asked you about it, because you have introduced a very high pressure and a very high temperature, and I think they have suggested you to separate the effects of the pressure and the temperature. I agree with them. I think it would be very interesting to know the effect of the different parameters, right? And you have already answered this, so it is okay. My question is, why 20 megapascals? Because do you know more or less the pressure that this material is going to be to support in the well? And in this regard, can you, after analyzing all your results, can you suggest some recommendation regarding, I would not use this material in the bottom because the pressure is somehow this value and it is going to break the spheres, or not? Can you make a general recommendation regarding the employment of this material according to the pressure? Because 20 megapascals seems very high. I suppose not all the well is subject to 20 megapascals. I don't know. I don't know if you can say something.
For that, I will go first to the very beginning here. So the general idea is to impose conditions in which the CO2 has achieved supercritical states. If we see that, we only need 7 megapascals, and that's it, and 30 degrees centigrade.
30, yeah.
Yeah, that's it. So I have kind of answered this in one of the previous questions, in which the idea was to continue the investigation research, or the research performed by previous PhD students, in which he used these conditions here, which are the conditions found, in particular, deep reservoirs located at more than 2,000 meters, which is far enough to attain these conditions. So, well, I mean, the idea was to continue this work with new materials, with this holograph microfiber cement paste, and that, and have more amount of experimental data in this context. So, as for the other recommendation that you suggested me to say, yes, well, of course, I do think that's a very important result that I have obtained is this related to the oceanic activity. Why? Because of the consumption of the outer shell of the glass of the spheres, which will affect the strength. Hence, I think that if we are able to measure this, let's say, degradation, or I don't know, this reduction in the thickness of the sphere, we would be able to see at what point each of these class of spheres is possible to be applied to some particular pressure conditions. So, as far as I have now, the results that I have now, I would say, in general terms, that, for example, for the results that I obtained, and I will show you them here, give me 1 minute. There. So, as for the result that I obtained here, I was able to see that the spheres 27 were already starting to break. This pressure corresponds to, if I remember well, it's around 15 megapascals. Accounting also for the oceanic activity, I would recommend, if I don't have the actual number, to apply them to pressures even lower than 10 megapascals, to have some idea that they will reduce the thickness at some point. Then, for the blue ones, which start to break at around 25, 30 megapascals, and the maximum slope here is reached at 35 megapascals, I will recommend something similar, but with this adaptation of the values. So I will go like to 15 or 20 megapascals, and there I will say that we are safe to avoid this rupture of the spheres. But for this, I have to say that it will be very interesting to assess the consumption of the outer shell, which could be possibly done by nano-indentation. And with that result, we were able to have more precise results in this possible application.
Okay, perfect. And my other questions, I don't know if it has been already done, is about another possible tests like capillary absorption to confirm the interconnection of the pores, or even permeability test to this kind of phase. I don't know why you have avoided this kind of test, or it's a matter, I suppose, that you start a research and it is difficult to develop all kinds of tests. But this test, in this case, regarding to confirm the MIP results and the rupture of the hollow glass, I think they would have been very suitable.
I mean, yes. We didn't receive, I think it was not for this particular test, but there was some similar comment from Fabri here regarding the use of other tests to measure permeability, diffusivity without breaking the spheres. And that's the idea in general terms. And well, yes, of course. As you said, it is not possible to do everything, but the main issue here was that we didn't know that we were breaking the spheres.
Yeah.
So at the beginning, now, yes, of course, it's kind of intuitive, but at the beginning we didn't know. So we saw that peak there, and we thought that maybe that's related to some I don't know, some difference in microstructure of the cement paste that's happened due to the presence of the spheres. We're just trying to understand these results because it was quite difficult. And when we obtained this idea of breaking the spheres that was perfectly aligned with all the results that we were obtaining, it was already too late to keep doing tests, but I completely agree that it would have been great to have done this kind of test to verify all these, all these supposed, let's say, improvement in the compactness or enhanced compactness of the same matrix due to the use of spheres. Totally, yes, I agree.
Okay, in a future research, I suggest you going on with this now that you are going to be a PhD, a doctor. In future research, maybe you can go on with this work.
Totally. Yes.
Okay.
Totally.
And finally, my last question is about the environment. You are working in a very the quantity of CO2 in your test is very high, and we have developed some tests also in this kind of environment, and we have detected that at longer ages there is a dissolution of the calcium carbonate because the acidic environment predominates over the carbonates, and so the precipitation of calcium carbonate ends in a dissolution. So I don't know if you have detected something like that in your test or not, or maybe because it is not very, well, 120 days, it is longer ages. So maybe you can say something, you have see something related to this?
Well, yes, I know that the dissolution of calcium carbonate is quite an issue that has to be assessed. As for the test that I have performed here and all the results that I have, it could only be an idea, and I didn't have much results to show that the dissolution of calcium carbonate was happening. But we know that at these conditions, at some point, it may occur.
Yeah.
I did think at the beginning that mainly with this cement paste, with the weaker spheres in which the carbonation is, the front of carbonation advanced is easier, let's say. I started to think that maybe there was some kind of dissolution of calcium carbonate, but then I saw the same images and I saw there a lot of calcium crystal precipitation compared to reference results. So I said, okay, no, it's still not happening, but I know that it could happen. In what I have obtained, I didn't see it, but I know that it can happen. And I also, well, it will be interesting if we find that this happens in the cement paste. It will be also interesting to add that into the model, of course. But
yes, I think so, because it happens at this high concentration of CO2, it has to happen because the acidic environment predominates. So I think so.
Yes,
yeah.
Yes, I agree. Yes.
Okay, I have no more questions. Congratulations again. It is a very impressive job, and I said to you, you must publicate the results because it is really important. I don't know if you have some publications, but if you have not, I suggest you, I encourage you to publicate because it is a very interesting job.
Okay, thank you very much for the encouragement and for all the words you took for me. Thank you very much.
Thank you.
Okay, thank you. So I think that's it.
Should I be worried?
No. Because I don't know where is the problem. One question about, but in fact, somewhere I wrote it in my short report, because in the end I was really annoyed because I didn't know in fact, like where was the problem, but because and it was sometimes difficult for me to understand between in fact the ways of some pore size diameters, because on some figures you can see there is a shift of the peak of the pore size distribution to 10.
Here, you're talking about this.
10 nanometers.
Are you talking about this one?
But elsewhere it was written that there was also carbonation precipitation, and so in fact it was in the end. So is there any problem? And so that in fact it's true that in your modeling there was a question of the crystallization pressure effect, but the answer to Antonio this was not taken into account because it's more to treat it difficulty. So I have another question. It was about the use of the micromechanical modeling to estimate the properties of the whole CS first of all, the results you obtain with perfect interface analysis is quite good because 60% of the was. I know that in civil geo, for instance, it's very good.
Yes.
But well, I was concerned because you made the job for running the modeling with imperfect interface. That gives you better results and almost perfect results for the shear modules.
Yes, true.
And so I didn't understand that why you did not use this afterwards in your bone mechanical modeling.
Well,
So is there a problem with the interpretation of the calibration of your interface parameters?
I think
or-
that there is a problem in the manuscript. I write something possibly that is not, what's the word? Clear. And so, yes, I did use the imperfect interface model. So maybe I wrote something wrong there, but I did use the imperfect
The
interface.
imperfect.
Yes,
Okay.
yes, because
So
of this
maybe
result.
it's me,
No, it should be me, I'm pretty sure. Yes, I will have to take a look at that to clarify it and correct it if it's corresponds. Of course. Yes.
So now I have a question. After have you done this work? How to say this? For you,
Yes.
how much continuum will you have or will it be if you have to do the same work for another cement paste with maybe different kinds of spheres to predict the behavior in supercritical CO2 storage device.
So you are
Do you understand my question? Because you have used you have combined lots of experiments on given materials.
Yes.
And you combine this with you have made predictions, and to do this you have calibrated some complexity. You have used some results data from the experiments. And now my question is, if you had to do this again for similar products, how much continuum?
You mean in this? You mean just to be clear, I will go all the way down, no, not that much. Here, you mean here, right? Or
Not
original-
necessarily. It's a very general question
general
about
questions?
the work
Okay.
you have done.
Okay.
Because I repeat, you have run lots of experiments with data. You have fitted this data. You also have calibrated some parameters to do the prediction at the end.
Yes.
For mechanical logic. So my question is,
Sure.
if you had to do this again on a similar program with different spheres or even cylinders,
Well, I mean,
how much
it's,
confidence?
yes, okay. So I will extend a bit more than just saying the confinement, if it's okay. So I will just say that if we already know all this and doing this now from now on state of the art, I will say, okay, we know about the positional activity. So I would like to have a way to measure how the spheres are affected. If we know that, then I will be able to say the confining pressure that I will use in my cement paste. So, for example, if I use different dosages of cement paste, but with the same classes of spheres, I think I mentioned it before. For example, I can do something else, but this idea arose during my PhD, so that's why I'm mentioning it. I will do some non-indentation test to see the shear thickness of the spheres. With that, possibly I could obtain the strength and how it decreased with the positional activity. And then I will be able to determine this pressure, maximum pressure, let's say, that I would apply during my experimental program. If I don't have this result, I would just say around, but this is a bit ambiguous, let's say, because I don't have the number for this. But if it's only on my mind and what idea I have, I would say like 10 megapascals or 5 megapascals less than the results that I obtain on this powder samples. So if I go, wait 1 minute, if I go somewhere over here, there. So there, this for the, well, this, the color changes, but the blue one is the HMS 27. It starts breaking, or the main peak is at 60 megapascals. So I will go somewhere between 6 and 10 megapascals, let's say, more or less. Not more than that. Then for the red one, which in this case is the HMS 41, the one that is stronger, the main peak occurs at around 35 megapascals. So I will go between 5 and 10 megapascals less. So I will go between, I don't know, 20, 25, 30 megapascals in that range. So with that, I will be more or less, let's say, safe that I'm not breaking them. But to properly say this, I have to measure to what extent the outer shell is affected. I don't know if with this I answered the question, but
Okay.
yes, okay.
Okay. So I have written some remarks on the description of the series. So I congratulate you for this work. I appreciate it.
Well, good to hear.
And yeah, you have the impressive work. So congratulations.
Well, thank you very much. I will also have to thank now, then I will thank a lot of more people later, but both of you here and Teresa and Siavash present in the Visio conference for the manuscript.
It's not finished.
No, I know. But well, as he said about the manuscript, I had to say that. Sorry. I wanted to finish. I'm tired. Sorry.
So next is
Okay, hello, can you hear me?
Yes.
Yes.
Okay, good. Thank you very much. So I could more or less with a good quality follow the presentation and more or less the discussions. So I would like to first thank Diego and Jean-Michel, who gave me the opportunity to be a part of this project. It was a nice project, but in which I had quite limited contribution, mostly in what concerns the micromechanical modeling, and during which I had we had very close interaction with Christian. That was very fun working with him, because I had the idea of this model since a couple of years, but I was waiting for somebody who come with some experimental results, and that was Christian. And it was very nice, and so we would be very happy to do this. So as he told that he is already tired, I will not ask him questions, but I would like just to say just first congratulate him for the nice presentation. I really liked it, and that was again much better than the repetitions that we had before, and more generally for the beautiful work he did. That was really Christian. That was really fun to work with you during the period, and also that was very fun to play football with you. I very much enjoyed it, and with this, I wish you an excellent future, and hope that we keep in touch and we can collaborate in the future. Thank you very much.
Thank you very much, Josh, for your words. Well, yes, it was very nice for me as well to work with you, and I enjoyed the article that we were able to publish together. So thank you for that.
Okay, thank you, Elizabeth. Professor Teresa Piquet. Are you there?
I'm here, yes.
Yeah.
Oh, shit. There. It was blocked. Sorry about that.
No.
Well, congratulations, Christian, for the excellent presentation and the work. We've been working with Christian since, I think, 2017. Also, we started working with these microspheres in what was, let's say, the master thesis, and we had these doubts concerning about the puzzolanic activity. And well, this is the part where we were able to work together at the Universidad de Buenos Aires, and we are also were able to publish this. He developed all these different tests and adapted them to be able to work with the microspheres. It was quite a thing. I think that there was a question about the superplasticizer. We didn't want to use it because we didn't want to have any extra additive to alter anything, but it was impossible not to. They were impossible to mix. It was quite a challenge to adapt the mixing methods to use this huge volume of microspheres, which was the one he found it wasn't on literature. So well, at the beginning to design all those mixes was quite a challenge, and Christian overcame it by mixing a lot. Mixing he did a lot of samples, and then he was able to transfer them to France to be able to carbonate them and to study them on the hard state. So I don't have much questions. We've been asking questions for the last, I don't know, 5-6 years. So, and I think he came to this great manuscript and this great presentation also with these publications, and I think he has more to publish now that he was able to finish this part, this very important part of his PhD. And so that's it from me. Congratulations, Christian.
Well, muchas gracias. Thank you, Teresa, for everything, and also for the work that we have done together, and the articles and the chapter of the book that got published. So
yes.
Yes. So thank you very much.
Forgot about that one.
Yeah.
Yes.
Okay, thank you. Now, Professor Diego Universidad Politécnica de Madrid.
Also visiting professor at University of Patagonia. First of all, congratulations. You know that for me it was a privilege to accompany you around.
I'm
Yeah,
sensitive, that's my part, to get sensitive, not yours.
I think I met him thanks to Teresa, because it was in 2015, Teresa. You met me, I was reading the emails just in order to remember what's happening in the beginning. It was in 2015, Teresa introduced him to me, just in order to work in his master thesis. Teresa is a specialist in cement, and I was working more in numerical modeling at that moment. So we do a team for the master thesis. So I want to thank Teresa at that moment. Was a lot of time.
Yes, quite a lot of time, yeah.
To now. But that was the first point, as Teresa said, to use a glass microsphere as an additive to lighten all those cements. And I would like to thank one person, I'm not sure if it's there, but what is interesting, the first seed of the research was thanks to doctoral Nadia Vasquez, who was a very good woman who helped us, Teresa and me, to develop this research. At the beginning, she was with me in a meeting in the former in the company Waytech when it was at the beginning in the 2014. We met there, and Morris, I think, is Teresa, the name of the guy who works in cement in YPF, which is the Argentine enterprise. And he said, we have a problem in the wells in Neuquén with this problem of we need to lighten the cement well. And he said, could be interesting to study this glass microsphere. So if we can, so Analia took this idea and gave a research project that you began to work on that at the project. For me, I was impressed, and also Teresa, I think, is impressed with your dedication, curiosity, kindness.
You're not be correct.
I think your career was very good, all your time. I know there was a lot of strength, sacrifice, as you mentioned in your acknowledgement. I know there was bad moments and good moments, but I think finally all these things give you growth, not only academically, but also personally. You are more self-confident of your capabilities. I remember at the beginning you asking many things if it's correct or not correct what you are doing, but now you are more self-confident. I think this is huge as you increase all your capacities, especially, well, you know very well all the tests that you did all these tests. Nobody helped you. Of course, there are many people who help
Yes.
in ETPM and also in the Vodafone, but you did the test. That I think is very good. And also you develop this improvement in the code of modeling. So I think you increase several topics of the PhD, but also the personal work, which is quite important. When he finished his master thesis, I remember that I would like to say that because it's sorry for that. No, but it's my opportunity to tell all this to him. He was finishing his master thesis and he began to work in an enterprise. For me and Teresa, I think was the worst things that he can do at that moment, because we are thinking as a PhD student at that moment. But he decided to go to an enterprise, and I remember was traveling to Buenos Aires, and I met you in the laboratory of the Sueros,
Yes.
And he was overwhelming of this work that was very stressful. And say, I'm thinking to continue further studies in the doctoral thesis. But at that moment, we didn't have any funding.
May I add something there?
Yeah.
I remember receiving mails from you and Teresa saying, hey, you have a PhD position that you can go in England, in Australia, in there. I was in this work, which was awful. Yes.
was studying this,
Yes.
but finally, Teresa and Analia has a project, a national project. We began as engineer working on that project in 2015 regarding this topic, and also with the topic of Tom Cruise, which is related with nanocellulose, this lithosphere, and lithosphere. So I think your journey was very interesting because you began little boy, now you're a very huge human man. So you did a strong path in this thing. So I write some ideas that I would like to mention, but just in order to. I think one thing I need to say, he obtained the Eiffel Scholarship. He won a really an award for the Young Researchers Conference. Once you complete the PhD student, thanks also for the National University of Patagonia. We have at the beginning, when we planned this thesis, was the idea to work with Jean-Michel and the Universidad de Buenos Aires, but thanks to Dr. Adriana Pajares and all the group of the academic commission that are present in the Zoom, they give us the possibility to continue your PhD thesis at the university. I think this gives us the possibility to continue with the Eiffel scholarships, and it was
quite a moment. Yes.
Quite a moment in our history. I want to thank also Jean-Michel, because without Jean-Michel, this project it wasn't possible, because he gave us the possibility to work with him in the École de Pont, give all the lab to us to study whatever we want. So I think without him, it's also this project can be possible. One thing once we recover you, the first things that you did when you came to Paris, go to the hospital. I'm not sure if you remember that.
Oh, yes.
That was happening a lot of things. He was in pandemic. We during the pandemic, he traveled here. He was 14 days in
Quarantine.
In
Yes.
the hotel. And the first day he came out from the hotel, go to see a football match, and he became with COVID and go directly to the hospital in July or June of 2019.
I think it was, yes.
So
not 2021. It was already.
21.
Yeah.
It's true.
Yeah.
21. That's all the things that happened during the
Yes.
PhD. So,
Without knowing in French. I only spoke a little French, and I went to the hospital and said, "Okay, you stay here." Okay. Where is it?
no, I remember that.
I do.
So he has experienced several things. The pandemic was one of them. Going to the hospital, another one, but also all the high mark that you have in your PhD. You have two articles right now, and we think that you can obtain other two in the near future. I think it's important to finish that. I'm very proud of your journey. Yes, I think I'm part of this.
Of course.
Congratulations.
Well, thank you very much. Thank you very much. Well, I think it's not my time to speak, so I will save that for later. Yeah, yeah, that's it. Thank you very much for your words. Very good.
Okay, that's Jean-Michel Pierre, Professor Physics.
Thank you, Mr. Chairman. So, well, I will be brief. Also, we want to rest. And Diego said a lot. I share a lot with what he said. First of all, I want to thank the jury, all the members here and online, for having spent time to work, to read your manuscript and to participate in this discussion and to prepare some unforeseen reports for some of them. Sorry for that. But thank you. I think it was a nice discussion. It shows the interest of the work. It's a huge work, a lot of results. You struggle all your PhD to have all this. Again, I think we end up with very nice results. Quite complete and consistent work, even if we, during the discussion, we can get some ideas and we see some of the defects, but this is the research, and so this is normal to have this kind of comments. So I think this is a very good peak. On a more personal point of view, I remember the time when you came here for the master thesis. Well,
I was thankful. Yeah.
So I still remember. So but yes, yes, I wanted to mention this, that you came here, it was difficult. I had to write a letter to allow the customs to let you frontier and port.
Oh, yes, yes, yes. Yes, it was.
We were in a rush with the disaster project.
Yeah, it was everything together.
Yeah.
And also I was coming with the specimens. I had like 140 specimens of cement. So a bag filled of specimens and so yes.
So well, this party explains why the curing was not done at the same condition, but it was not done in the same hemisphere. Not only the pressure, but also the hemisphere.
Yes.
But yeah, on that you started. Yeah, I remember that you worked a lot. You started on build at the time.
In 2017, yes.
And in the end, you finish with build, not on the same material, not on the same results.
Yes.
But so you spend a lot of time on this code, but in between there is all this experimental work. I think in the end you characterize more or less well, and we understand what we learned. You have been very, very tough in doing your experiments. Yes, I want to insist on this point because it's never easy to the results come from many places. I think the same images are from other places.
Yes. Yeah, it's a mess.
Yeah, so many groups with whom we interacted to get all these results. So and we work very independently. You say explain that these are his results and the fruit of his efforts to get these results. But yeah, in the end, every project should end up. I think it has been a mess to finish all this.
Yes.
To complete the writing, to find all of us to read it. But I'm very happy with the impression that people have. Very and the presentation, and I'm very happy for that. But I think you should be proud of it. In the end, this is your work, right? So you have to be confident and proud of what you have done. It was a real pleasure to work with you. So, and of course, with my colleagues. But yeah, I was very happy to be part of this work. As far as I could. Thank you for this.
Thank you very much for your words as well, Michelle. It was also a pleasure to work with you here. Yes, it was tough at the end, but well, finally we work here, so it's nice for that. Yes, it was a hard and long journey, but well, I mean from 2015, you said? Yes, so well, I will speak later, I think. I will leave that for later, for my turn. Yes. Thank you very much for listening.
Okay, so we have finished this discussion session. Except if you want to begin again.
I mean, yes. To begin with.
You are in Zoom.
Yes, I am in Zoom. Yes.
We have to move to maybe it's closing.
Sí, esa es la presentación. No sé por qué hice si no veo nada sin los anteojos, me hace llorar. Ahí está atravesado. No sé qué quieren hacer. ¿Poner un grupo pequeño? Ah, bien. Lo que vamos a hacer es, vamos a cambiar esto. Teresa y Sebas. Perdón, me agarré.
Sí,
Ustedes pueden.
I think you have to talk in English if
can
it's
you
also
move-
for Sebash.
Para mí el castellano es perfecto.
The problem is that we have to move. Okay. You want me to move the?
There will have
Should
there
we
will
go
be
to the?
a new session.
I think there's a breakout room
Yes,
that
there is thesis
is
evaluation.
inviting us.
To put unirse in Spanish or
Yeah.
join in English, and we have to. You have to go out. Yes, I know.
But how can I join this room?
Yeah, ma'am. Oh, here it is. There is if you go to the 3 points,
Yes.
there is the last one. No, it's not the last one. Sorry, the third one. It's well, in Spanish is salas de grupo reducido. Maybe it's closed room places.
Also,
You will enter there.
Profesora Maria Belén, you have to. Maria Belén, you have to also. Maria Belén is also in the room. Teresa, you are not yet.
No, but Sebash, did you find it?
No, but no, because I'm on mobile phone, so I'm looking for this.
I can move you to the room.
It is.
I will move.
Okay.
Please, Diego. Please, Diego.
I move also Teresa now. Oh, it's okay. No.
Okay.
Just give me a minute because I have to join for another computer and mute this because if not, the people who are online are listening. Give me that's it. El link del Zoom para yo conectarme directamente en un instante.
Diego, vos te conectás directamente entonces de esa computadora.
Yo me conecto, pasa que para poder hablar me voy a conectar desde mi computadora, ¿sí?
Recuerden que esto queda abierto.
Por eso.
YouTube sigue transmitiendo esto.
Por eso, tenemos que, ¿cómo hacemos para...? El problema es que nosotros estamos en la misma sala. Bueno, voy a ver cómo hacemos. Si vos te pones ahí...
No, pero si vos muteás esta computadora y listo. Muteá la computadora que me está hablando ahora y no se va a escuchar nada. Se va a ver nada más.
Perfecto. Claro, cortamos el video y el audio.
Y listo.
Este es el Zoom. Yo ya me tengo que ir, ¿no? Dame un segundo antes de irte porque veo que tenga algún problema.
Felicitaciones, Cristian, si estás ahí.
Muchas gracias, claro.
A ver, muestra la presentación.
Todavía no sabemos, pero que ahora tengo que encontrar yo.
Listo, ahí está muteado.
Ahora estamos. Está, listo. Ahora sí. Ahora me tengo que ir yo a la sala. ¿Cómo era esto? Mira, me voy a poner de acá, digo manzana sonido y me mando de acá. Vamos a ver, listo. Ahí están todos. Un segundo. Ahí te mandan. Bueno, pues,
Ah, une monnaie, il a dit. Ah, il y a des
On met les volumes ahí y lo llamo a la gente.
No, mais. Non, non, Diego, no está.
Sí, están todos, están todos.
No, thesis evaluation. No? Can you hear us?
Teresa, María Belén, you can
Yes,
hear
yes, yes. We
us?
can hear you. Yeah,
Yes,
yeah, yeah. That's okay.
Yes,
Yeah, it's okay.
yes.
No, no, espera, el sonido se acaba.
The volume, where is the volume?
It's okay. We can hear you.
Apretaste algo acá.
No, es él.
Ouais, c'est mieux que ces écrans qu'il y a bien.
Ah, on sentait qu'il y a des
Can you speak? Yeah.
Yeah. Yes.
Yes.
Can you hear
Okay.
me?
It's back. It's back. So we are calling Christian and.
Okay.
Okay.
C'est pas un écran, non, c'est pas un écran.
Non, c'est projeté.
Ah ouais. Ils ont mis 3 morceaux. Et c'est comme le mec qui roule dans un café d'Asia.
Todos pueden escuchar. You can hear me. Okay.
Yes, yes, that's okay.
Perfect.
Claudio, are you there?
Yes, I'm here.
Okay, great. Great. You can wait 2 minutes. Coming.
Okay, yeah.
Sorry.
Yeah, no,
No sé si van a ver o no, pero es para ver aquí.
Ah,
No sé si
il faut que Harry se mette comment ça c'est une webcam.
Ouais, mais c'est pas grand-chose.
Et donc il faut qu'il se mette ici. Hein.
Je sais pas. Ah, ¿Dónde está lo que ven ellos?
Ouais.
On fait l'inverse, nous, ils n'ont pas besoin de le voir. On se met là.
So, ok, vous voulez que je mette la caméra par là ou...
Non, peut-être pas comme ça, nous autres,
Bueno.
Non, c'est pas mieux. Oh, c'est important. Ok. Okay, everyone is ready. No. Okay, so Mr. Christian Marcelo Martín. So the view has so we make 2 appreciations. And the first part is about your presentation and the questions. So we like your manuscript, and it was great quality. So we have also greatly appreciated your presentation. And you have perfectly summarized the main results of your work. And in addition, we know that you have worked on very diverse fields, and you were able to work on some of the parts and so this is very grateful about your discussions. So we also appreciate the way you have answered to the questions very properly, and you were also able to have fruitful effect in the and again it was on very different diverse fields and works with very so so I'm not sure if you know this works. And so now the final decision. So the jury, so once you and Universidad Nacional de la Patagonia, San Juan Bosco.
Yeah, it's better than it was now.
Ah oui, pinceau.
Choose the French. Choose the French or the English.
Well, I think for everyone, we're ready to English. There's no Spanish version. So I will try to do this video. So, in the process of 5 years, with the completion of my doctorate in geotechnique, in my quest for knowledge, I have carried out demanding research, demonstrating intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. I speak?
Yes.
I can't speak. It's fun to be here now, you know. I have waited for this time for quite a long time. So I don't have the words, which is kind of weird. So I will begin by thanking the members of the jury, which were in case of mainly, I think, you did a trip to come here. So thank you very much. Also, you, Diego, you came from Spain. So thank you very much for that. Thank you as well for the president of the jury, Michel Pereira, for receiving me here. Antonio Fabi, you were already here, I think, but I don't know. You came from Lyon?
Lyon is not so far.
Okay.
2 hours by train.
Okay, well, yeah, but it's a trip already, so thank you for that. Thank you as well for those of you that were not able to be here. Maria Belén González Fatego, thank you very much for reading the manuscripts and the questions that you have done me, also that for all the jury members. Also, thank you very much to Siaba Chavez-Lo for co-supervising this thesis and working with me at some point. We did my mechanical modeling. Thank you to Teresa Piqué, of course. We have started this in Argentina with her mainly, and this first part was very difficult, but then we achieved some very interesting results related to the interaction between spheres and cement, which were really interesting, and we were able to publish, as I said before, the article and the chapter of the book, which was awesome for me. Then, of course, thank you to Diego, well, Jean-Michel, as I said before, with both of you, and also with Teresa. I was able, in fact, to do this research project. I was able to do all these trips. Yes, I didn't know if I wanted to use that word, but it was quite an interesting PhD in that part as well, because I have traveled a lot. I was in Argentina, then I came to France for 18 months, went back to Argentina, and then went to Madrid for 3 months, then went to Norway for another 3 months. So this was quite really enriching for me myself as a person. So I really want to appreciate that and the effort that all of my supervisors, Teresa, Diego, and Michel mainly, did on this, to obtain the fundings and all that. Well, I have already mentioned this, but I really want to thank the technical team from both the Universidad de Buenos Aires and the Instituto de Tecnología, Información and Tecnología, the institution founded by Analia Vázquez, we mentioned before. And there they helped me a lot. And of course, here I can't really see because of the light, but it's there. But maybe Marine is somewhere there. I don't know what. But thank for to you too, Loic as well. You helped me a lot throughout my experimental parts. So thank you very much for that. Oh, she's here. Okay, thank you, Marine. And well, I will now go to the more sensitive part of this speech. There is acknowledging the support that I have received throughout this whole journey, which was very tough at some points and very long as well. I have received support from many different parts, beginning with from my friends at the beginning from Argentina, the friends that I have since I am very young. There, at the beginning here it was quite crazy. We here during the end of COVID, so I found something there to talk to, someone there to talk to, and that was very necessary. Then I was very lucky to form what we call La Familia here in Paris. Well, there are many that are not here, unfortunately, because of trips due to the Christmas and the end of the year and that. But well, that was incredibly important for me. We formed a really nice, beautiful group, which I really enjoyed a lot to share this moment with. It was amazing for me. And well, I remember that last Sunday, we have the last dinner with Pablo and Fred, which are like two of my best friends, and it was really a sensitive moment for me. Well, I talk about friends. I want to talk also about the colleagues from the Instituto de Tecnología, Progreso y Tecnología, which I think many of them are watching this from YouTube. So thanks to you as well, because you are a very important part of this. Thank you also, I think I will finish with this, to, well, my most important supports throughout this whole my life, which is my family, which were able to come here. So I want to avoid this, but well, so thank you very much for being here. No, it's not easy. You did a really huge effort to come here, so thank you very much. Thank you as well to Paula, which I hope at some point you are part of my family now, so thank you very much for being here. And well, to all of those that I maybe forgotten because of these moments, sorry, but well, thanks to all of you. You were, every one of you, a very important part of this, so that's it. Thank you very much. Yes. No, we don't have any rules, sorry. No, okay. Yes. Thank you, Diego. So now I invite you, for those who are here, to go to the room P12, which is like in the end of the corridor here. There you will have the opportunity to taste some Argentinian things and also Italian, because I'm partially Italian. So there you have a bit of everything. A bit. So you have alfajores, which is something sweet, and you will have also empanadas, which is something not sweet, salty. So well, there you go, and you can go there and enjoy this meal. He has the keys in my father, so follow him. That's thank you very much. Thank you.
Thank you, Maria Belén, for
Thank you for the invitation. Hope we can get together in present somehow. And good Merry Christmas that are near, that are close.
we need a photo. We need a photo.
Okay.
Online people also.
With the online people. So how to do it? Online? Like this, but how we can just a photo?
I think you can change the way you can the image. So instead of seeing the one that speaks,
Yeah, the screen.
you can see the block.
I need to know how to do it. Let me check.
You go to
Because
hay un cuadradito arriba a la derecha que tiene que dice ver
Vista. I think it
o
is.
vista.
A ver, dame un segundo.
Es arriba, en mi pantalla es arriba a la derecha.
Arriba a la derecha. Vista, acá está,
Bueno.
gracias, ahí está. Varios oradores, a ver si esta sale. ¿Ahí está bien?
Ahí estamos, sí.
I think so.
Moi, je vais être derrière. Comme ça, on aura l'impression que
Tienes que estar en el centro.
Debería, ¿no?
Vamos.
I think it's better to stand in the middle because the light is quite.
We have Sebastian here. Maybe we can hide our camera and then Sebastian will go up. I'm not sure if it's possible. Si solo lo cerrás la cámara, tal vez va arriba Sebastian.
Creo que puedes ocultar tu imagen propia.
A ver. Dice, ajustar, eliminar anclaje.
Eliminar anclaje, sí.
Es Christian here, eliminar anclaje.
Hay una forma que es ocultar participantes sin video y ocultar vista propia.
Ahí está.
Gracias, Teresa. Now it's okay?
Yes, exactly. So where are you put it there? Okay.
Ahí está.
Sebas is cool.
I'm here. Can you see me normally? No?
It's okay.
Yes, okay.
The people are eating all.
More,
We need empanadas.
Yes.
How many pictures you take?
Yes.
Thank you very much, Teresa.